In the next subsection, we'll look at some lower bounds for what you can possibly achieve with codes. And the goal was to have codes that can detect or correct errors, or maybe both, right? I motivated last time a bit why communication, even for a computer where things are stored in binary, has noise sometimes. And just as a reminder, we'll look at specifically the type of noise where one bit can be flipped or twisted from its actual value to the negation. We won't look so much at other types of errors, although they are potentially also relevant. But in the situation where you transmit some signal over a wire, where the timing is somewhat given, and just the value that you receive is disturbed, that's the right model to look at. So we'll focus on that. And we'll start with, as always, lower bounds are proofs about what's possible. So you have to say, what are all possible things? So we'll start with formalizing this a bit. So our model will be as follows. We start with the source message S. That's an arbitrary bit stream. So remember, this is just a string over that alphabet of arbitrary length. And we have some communication channel, which will basically just mean that whenever we send something, any bit could be flipped. So instead of S directly, we will send the encoded version of S. Hopefully, adding enough redundancy to correct these flips. So instead, we'll actually send C, so another string. That's the same notation as in the compression unit, but remember, the goal is the opposite. We're not trying to reduce storage space, we're trying to add redundancy in. And then there's two functions. We need to encode and to decode. Encoding happens at the sender, decoding happens at the receiver, and hopefully they get the same answer. All right. That model is overall a bit too generic to make any interesting statements. So instead here, we'll focus our attention to block codes. And all that means is that instead of sending the entire string here of arbitrary length, we only look at m bits at a time. That's a block. So we'll send k bit blocks over from the source text. But what we'll send will have more bits, namely n, and that's what comes out of the encoder. So I'll just write this as C of m here. So C is the output, the coded text, and the function that produces that. I hope it's clear from the context in each time, whether it's the output or the function that computes it. Now, of course, the way you use this is, as you would obviously expect, you take the first k bits of your source message, encode that in the first n bits, send those, then you go to the next block. And the receiver inverts that in the obvious way. It takes n bits that they receive, then they decode that to k bits, and then they go on to the next n bits that are received. This works perfectly if you never ever lose bits. If there would be a channel that inserts or deletes bits, then you might miss what the block boundaries are, and then you have to work around problems there. Because we don't look at that, a block code is essentially general. There's nothing lost by looking at things block-wise. If I send a block of n bits, anything between 0 and n bits might be flipped. In an actual scenario, of course, we would assume that it's not so likely that all the bits get flipped. But we won't get into the probabilities here. All that we show is essentially worst-case results. And we'll make guarantees what the codes can do. And if there's more things flipped than they can handle, then we won't receive the original message. And so again, the two things we try to do is detect and correct. And the question for a block code then will be, how many bits can we flip to tolerate so that we can still detect there is some error happening? And how many can we flip so that we can still correct to the original message without retransmitting? Okay. there's one key property of codes that only becomes possible by looking at these block codes, but that will be very useful. That's the notion of code distance. So here's the first simple observation. If I have an encoding that takes two different source messages and maps them to the same coded text, the same coded block, that can never work because it's impossible for the decoder to, even without errors, to know which was the source message. So the encoding function is always injective. It produces different outputs for different inputs. And that means we can't have an arbitrary number of those. So let me be more specific. If we define the set of code words curly C as all the code words you obtain, so this is the set of all n-bit strings. So it's the set of all blocks, so that there exists a message in the of k bits, which produces this block. Then we call that a code word. So it's all bit strings that you can obtain from a message when you encode it without any bit flips. Now, because of this injective property, it means for every message I have a different code word. So I have at least as many code words as I have messages, and I only have so many because I can't have more. There's no others coming around. So the size of the set of code words will always be the same. It's always 2 to the k, because that's the number of different messages I can send. But the code words themselves are n bits long. So I have 2 to the k n-bit words, or n-bit strings, and these are my code words. Now, if I define a coding function like this, I can do a generic decoding, which is, in a way, always best possible like that, where I say I just decode it to the closest valid code word. We'll see examples of this later. If you fix this decoding, which is, I think, a natural thing to do because it makes the assumptions that more errors are less likely. So you always decode to the thing that would have resulted in this with the fewest number of bit flips. Then you can define the distance of a code as the minimal distance of any two code words. And here's this notion Hamming distance. That's just the number of positions where these words differ. So in particular, if I had, just to practice that a little, I have a fun example. Let's do a boring example. What's the Hamming distance of those two strings? Should have prepared a Slido question. Well, we can just look at which letters are the same. So A is the same, and the last A is the same. But then these two are swapped. But for the Hamming code, all that matters is that this is different and this is different. So it's Hamming distance 2, right? It's 2 positions where the letters are not the same. Hamming distance is only defined if the two strings are the same length. So we never have to worry about what happens if one string is shorter. That's not a thing. So if I take the Hamming distance of all the code words, all pairwise distances, that's what this minimum is doing. It picks any two code words. I guess any two code words that are not the same. Otherwise, we get a 0. then that minimal Hamming distance, that's called the code distance. So far, that's just the definition. And I hope the next few slides convince you that it's a reasonable definition. And the first property that follows from this comes straight away. When I want to detect up to d-1 bits of an error, so if I want to be able to correctly detect that something went wrong for up to d-1 bits flipped, then I need code distance d. And the reason for that is simple. If there were any two code words, I'll draw them like this. I mean, they live in some high-dimensional discrete space, but I'll just draw them in the plane as an intuition. So it's done. This is not exactly to scale in any sense, but okay, and that's not the middle. Okay, sorry. For that picture, I should just put that here. So what should these dots mean? That's one code word. And that's another code word. And the distance between them here, if that is d, then I can definitely not detect errors where d bits have been flipped, not correctly detect. Because there's a way to get from x to y by flipping d bits. That's what the code distance says. The Hamming distance between x and y is d. So if I started with x, I had a message that produced x as code word. Now my channel flips d bits. Then I arrive at the code word I would have gotten for message y. And it looks exactly like the code word for message y. There's no way for me to know that I actually started with x and had these d bit flips and distinguish that from the situation where I started with code word y. So there's two possible explanations for receiving y. One is we send a message so that exactly gives you y as a code word. It is a code word. So if x and y are in this curly C, y is a code word, so there is some message that gives you that. Or other possible alternative universe, m was sent. The block for that is x, the code word, and d bits flipped. That's the proof why if you want to detect d-1 bit errors, you need distance d. You cannot detect d errors, d bits flipped with this code of distance d. At least there's one input where it doesn't work. That's the first part. The second is a little more interesting because that gets closer to error correcting, what the point of the whole unit is. And it says a similar statement. If you want a certain number of bits to be able to be corrected, you need a certain minimal distance. And the reason for that, let me draw a similar picture. And we will again have these two situations, A and B. So we send a message and then flip d-1. Oh, let me give that another name, flip t bits. So one option is I started with x and then I somehow went to x prime, which lies in a radius of size d, t. So imagine these balls are Hamming distance circles, which are more like weird squares or cubes, but it's nicer to draw it like that. And then the other situation is we have a code word y, running out of space here. Second situation is we started from another message, and then we flip to t other bits. But we end up at the same thing that is sent over the wire. So we in both cases end up with x prime. That would mean that x prime also lies in a circle around y of radius dt. Okay. So that means for sure here the Hamming distance of x and y directly is at most 2t, right? Because I can get from x to y by flipping first t bits and then more t bits. Maybe some of these flips are at the same positions, then the distance is actually smaller, but at most it's 2 times t. If you invert that statement, you get the claim here. So this shows you if the code has distance 2t or less. There's an instance where you can start from 2 legit messages, you get the code words, and you flip t bits each, and you collide on the same thing. So if a receiver receives x prime, there's no way for them to know whether it was whether it was m or m prime that was originally sent, because both have a way by flipping t bits to arrive at the same bit pattern. Okay? So if you want to be able to correct t bits, you need to have at least 2t plus 1 as a distance for the code. Otherwise, no chance. And if you invert that and write it nicely, that's the second line. So you need distance d to have d minus 1 half bits, and then you can say that's your t. Now, important remark, the way these things are formulated, they are correct, but they're only implications in the one direction. They say, if you want a certain number of errors to be correctable, your code definitely needs distance at least so and so. But it doesn't tell you that any code with that distance guarantees that you can correct errors. That's not necessarily the same thing. Okay? So as they're written, there are just implications in the one direction. But we're in the section on lower bounds, so we'll make statements like this in this case only. Based on this observation, there's 2 lower bounds that tell you something about specific codes. And I want to show you these very briefly, just because I think they're useful to keep in mind, and they're useful thinking patterns. So in this case, we fix the block length, and we'll fix the message length, and we fix the code distance. 3 parameters flying around. And then we'll have certain statements that mean these parameters have to relate in a certain way. Okay, let's see the first example, the singleton bound. It's by a person called Singleton, not that it's necessarily no other meaning of the word. It's just the name. The way it's easy to show is this inequality. But because it's 2 to the k to the n minus d minus 1, you can just take logs on both sides. And then you get this, you can rearrange to this nicer statement, which is more intuitive. If you have these 3 parameters given, usually the message length and the code distance is what you want to fix. And then you want to know, how big do my encoded messages have to be? How much redundancy do I have to add? And this bound tells you, okay, if you want a message length k and a distance d, you at least have to add those up and subtract 1. That's your minimum code length for sure. You definitely can't do better. It doesn't promise you that this is doable, and it usually isn't. Well, let's briefly prove why this is true, this first part. Remember what I said before about the code words? Every message gives you a different code word. Injective, encoding. So we can write down all those code words after below each other. And again, I'll just sketch this here schematically, not for any specific set of parameters. That keeps going. So these are your 2 to the k code words. And they each have n bits, right? Now we know more. We know that they have distance d. So whenever I pick 2 of these code words, I know there's at least d positions where they differ. Same notation as in the string matching chapter. The little bold is just there's a difference there between the characters. So if we now take the first d+1 bits, so in all of those, we chop off the first d-1 bits, and we now only look at the code words that remain after that line, okay? Because I only removed d-1 bits, and every pair of code words differed by at least d positions, there will be one difference to the right of the bar. The worst case would be if they all lie here, but then there's at least one more on the right, just not enough left. That's all that this proof says. It's a very simple proof. So if all of these 2 to the k strings are different afterwards, then we must have that the lengths relate like this, because there's on this side, the strings that remain are n minus d minus 1 long, right? In parentheses, the subtraction. And there's 2 to that length many different bit strings with that many bits. And we've just shown that they're all different, so there must be enough of these more than 2 to the k. Okay, that's the proof of the singleton bound. That's all there is. And it gives you this nice statement about how these 3 parameters relate. And it's particularly nice because it tells you straight away, give me k and d, and I'll compute you a lower bound for the block length. It's often not tight. Often you can't achieve that bound. You can't find a code that gives you straightly this. So there's a second bound, which is often a bit more powerful. And indeed, we'll see instances where we match exactly that bound. So in a way, that bound is best possible, or strictest possible. That's the Hamming bound. And this is more complicated. I can't easily give you a formula that, given k and d, tells you how big n has to be. It still has the same flavor. N is bigger than something. You can rearrange this, right? It's the same as saying 2 to the n is at least 2 to the k, and then times this lovely sum. Let me use this abbreviation t again. It's defined below here anyways. And I'll remind people that these are binomial coefficients. You should know what these are. Otherwise, ask Wikipedia afterwards. So this is also an inequality of these parameters, and it in a way tells you that n should be bigger than this, but it's a little less explicit. Why is that true? That uses, again, the picture from before. If we have our balls around a certain code word, then we know that the code has distance d. So if I go from here to there, I need to flip at least d bits. Right? And if you look at how t is chosen, it's the same as before. It's half of that distance, but rounded down if it's odd. And okay, I subtract 1 and then round it down. So I always make it strictly smaller than half. So the radius of these balls can be t, but they don't touch. The balls are disjoint. Okay? That's step one. Maybe I should put the whole thing in quotes. The quotes are just because it's not really round. But you can still imagine the set of all bit strings that have Hamming distance at most t. So that's what we'll do here. We count all the bits that have Hamming distance at most t from a given code word. And how many are there? Well, if you do this more seriously than in this graphical representation, okay, I don't know if I can draw this properly. Let me stick with that image. There's a few that are just around x at distance 1. These are flipping 1 bit. Okay, and I can pick any position in x. So any of the n positions I can flip. So that gives you the size of this set of things at most distance t from x is 1 for x itself, plus n for all the strings that I get from flipping 1 bit, plus n choose 2 for choosing any 2 positions to flip 2 bits, and so on. So I sum those up. F is the number of flip bits, and I can flip at most t. And these are all disjoint sets, so I can all sum them up. So we count these. That's the ball size, and that's this sum. Okay. Now, every code word gives you one ball of that size. Namely, code words, we know the balls are all disjoint. So every code word gives you a full ball of code word of bit strings that are taken. We know all the balls are disjoint. So if I sum up all the ball sizes, number of balls times how big they are, I cannot use any bit string twice. So that product has to be at most 2 to the n. And that's precisely what's written here. So that's a more delicate bound, but it's much more tight to what is actually doable to achieve a code with a small distance. Okay.